Welcome. Hello, everybody. My name is Dan Lawrence.
And my name is Breland Blake.
And today we're going to be talking about design for additive manufacturing and how we applied some of our knowledge and expertise to our project quadcopter. So before we dive into the DFAM, the design for additive manufacturing portion of it, let's first just kind of review what design for manufacturing is. So design for manufacturing is something you guys are all probably very familiar with and probably do it as second nature as a designer. But to break it down, it's essentially, it allows you to find and fix prudential problems during the design phase. So some very common, examples that you might do on a regular basis: designing for draft angle for your injection molding, right? You want to make sure your part comes out of the mold. Right. For milling, you want to make sure you avoid long radius corners, have enough relief angle, clearance. Same thing for welding. You want to make sure you have enough proximity that you can actually do the weld. Right. You also want to avoid distortion, so you want to have little to no angle between the components. These are all aspects and constraints that you're designing for in design phase. So that's design for manufacturing. And design for additive manufacturing is the same thing. It's actually a subset of design for manufacturing. So it works pretty much the exact same way. And as you noticed, for design for manufacturing, all of those were technology specific. So each process, each manufacturing process that you're working with and you're going to be using has its different in its own constraints. The same thing applies for additive manufacturing. As you can see here, these are three of the more and probably the most commonly known processes for additive manufacturing for 3D printing. You'll see a lot of acronyms when you work in this field, but I'll explain what all of those acronyms mean right now. So FFF right here on the left-hand side that you can see, and FDM, that stands for Fused Deposition Modeling. And it's probably what everyone thinks of when they think of 3D printing. It's the most common. It's 99% of hobbyist printers use it, and it's actually what Markforged, the technology that Markforged utilizes for their printers. So that's the process that we used and we designed for, which we'll talk a little bit more throughout this presentation. But moving on, we have SLA is another process. It stands for stereolithography. And the way it works is the build plate is moving upwards, as you can see here, and it's in a liquid resin that's being a light's being shown on, and it's kind of curing it. It's also going to have quite a bit of process, post-processing after, where you're going to have to put in UV light in order to cure it after the fact. And over here, DMLS is another one. It stands for direct metal laser sintering, and it's pretty self-explanatory on how it works, right? It directly sinters metal with a laser, as you can see here, as it's sintering, as this laser is being shot down onto this powdered metal, it's sintering it and it's creating the part. But that's the process that we're going to be using, right? Is FFF or FDM, right? That's what Markforged uses, and that's what we're going to be talking about for the remainder of this presentation. So Breland's going to take over right now, and he's going to explain how this process works and some of the considerations we might want to consider.
Thank you, Dan. So in this slide here, we're going to just explain really quickly how your 3D printing process works for an FDM printer. As you can see at the image at the upper right-hand corner, we're seeing the build filament building layer by layer. This is something that's produced into our slicer. The slicer prepares the print before the printer actually begins printing. So how a print is actually generated is it's printed on the bed plate layer by layer. And if you can think of an FDM printer is much like a hot glue gun. Hot glue gun is going to utilize a hot glue stick that's put into a hot glue gun. And the hot glue gun's heated up and push that hot glue through the nozzle, and then out comes hot glue. Much so like a 3D printer, your filament's heated up inside of your print head. It's heated up and it's extruded out through the nozzle, and it's produced layer by layer on top of your printing bed. So that's kind of the explanation for your layer by layer with a 3D print. Okay, and some of the limitations that we're going to look at here with our anisotropic and our transverse material properties, you have to remember that the XY plane is going to produce more strength if the printer is using the Z-axis to produce your layers. So your layers are heated up and they're built on each other layer by layer. The way that they get their strength is some of that filament is hot, so then they fuse together to start building and producing your different layers, and that's how your part is being built. But you have to keep in mind in your XY plane, that's where your strength would come from if your nozzle's coming down from the Z-axis coming down. So in our first image here, we're showing that our extruder is printing from the Z-axis. So our weak spot would be the Z-axis if we have any elasticity deformation. But if we were to take a part and turn it 90 degrees on our printing bed, and we would have that part just printing on a different axis. Wherever that force would be applied, you have to think about that, before your printing is actually done, because then you have your shear failure, and then the force that's applied with your shear failure, that's where you would fail when your layers either deform or you're getting a shear. Some other things that we have to look at as well with some of the feature fidelity in the X, Y, and the Z axis is that our print on our first image on the lower left-hand corner is going to be shown in the parallel to the build plate. So what that means is when we have holes that we're printing, 3D printing, it's going to give you more of a reliable print shape. So when that nozzle moves back and forth, it's going to give you a nice crisp circle. If you have any holes or anything like that, you have to keep in mind with your design intent. So that's going to be a more repeatable effect, opposed to printing on a different axis where that print, let's say you're going to print that same part and you want to represent that hole, your print nozzle is going to go back and forth, but in order to produce that circle, it has to produce those print layers. So those print layers are actually going to stop at the edge of those circles. It's not going to be a really nice crisp line, and you're not going to have a really nice round circle. So it's not going to be a nice repeatable circular structure there. Also, something you want to keep in mind is the process limitations for our support material. So you can't produce any prints that are just begin printing in mid-air. Your print layers are going to need some kind of support material underneath. So anything that is over 45-degree angle will need to generate some support. And that's all done in our slicer. So in the image at the upper right-hand corner, we can see that mark for each part, and it has a whole bunch of lines underneath it. That's the support material. Because that part was turned 90 degrees on the print plate, in order to start printing that part, you need something underneath it to support the actual part material that it's printing. So that's where support material comes in effect. So anything over 45 degrees, you have to generate support. Anything under 45 degrees, you won't need that support material. And that's something you have to think about as well, is how your part's going to come out. But also with support material, it's going to slow your print down. And it's also going to produce a lot of post-process work that's going to have to be done after the fact.
All right. So now that we kind of understand how this process is going to work, right, and some of the things that we're going to need to consider, now we can really start approaching designing the part. So this flowchart is very, useful when you're thinking about going into designing a 3D printed part. You could probably use the same flowchart for any engineering part. But let's look at these first two. Right. For our case, we don't really need to consider this, but if you're going to be 3D printing something in manufacturing, these first two are very, very, very important. Identifying your problem and estimating your business case. So for us, our problem is we don't have a quadcopter, and our business case is for this MIP event, essentially. But for manufacturing, right, your problem might be this part broke, and right, does it make sense to 3D print it? That estimating the business case is very, very important, right? So I want to emphasize that because we're not going to really talk about that too much in this presentation. But these first two steps are very, very important when you're considering designing for additive manufacturing. Right, once you've identified it and it makes sense to 3D print this part, then you're going to need to identify the functional requirements and design your minimum viable product. So essentially, this is the DFAM portion of the design process. This is all of the revisions and what needs to go into the part. You're designing it in CAD, which is what the majority of this presentation is going to be about. And we'll also talk about configuring and printing and some things to consider. And once you print it, right, you're going to implement and iterate, and most likely have a very fast cycle to iterate that, right? It's the whole, one of the main draws to 3D printing is rapid prototyping. But right, let's move on to identifying our functional requirements. So like I said, you're going to have some revisions that you're going to be doing in the design phase. So let's move on to our quadcopter, right? What you're looking at here is the first revision of both our frame and components and our canopy on the left-hand side. And after, you know, all of the revisions and considerations that we're going to go through and step through on the next couple slides, we ended up with our final revision, which we actually got to 3D print, and hopefully we'll be able to show you it at the very end. So without further ado, let's go on to identifying our core functionality.
So some of the core functionalities we had to take in mind here with this project is we needed a bill of materials. So we needed a parts list. So some of the parts that we wanted to keep in mind, we had to involve our design. And the typical design that we wanted to do with this quadcopter is we wanted to make a smaller racing quadcopter. So we wanted something light, thin arms, something that was going to be fun, you know, fun to fly, slice through the air. So with that in mind, some of the parts that we started with were the motors. We wanted to use high kilovolt motors. So we wanted to have it pretty snappy and pretty fast. So we had to keep that in mind. To pair with our motors, we wanted to go with some pretty aggressive propellers. So we had to keep that in mind as well. With our electronics, if you can see in our image to the left, it's an X design of our quadcopter. We incorporated some different bolting pattern features, which we'll go over a little bit later. But that will incorporate our electronic stack. And our stacks are our ESCs, flight controllers, and all of our electronics are stacked on top of each other. They're bolted together. So in the middle, we use our ESCs, which stand for electronic speed control. That's going to control our motors. The flight controller, we want to use different sizes of our flight controller. So we had to keep that in mind as well as the VTX for our camera. And then also the RX for the actual receiver for the quadcopter. We incorporated a neat antenna design, which we can go over a little bit later. We also had to keep in mind the placement of our camera and the battery for this quadcopter, which was actually mounted underneath.
All right, so now that we identified, right, all the parts that we need, we're gonna start looking into designing, right, things that we want to consider, what these parts are gonna interact with. So this first image right here is one of the first things that we came into, we thought about, right, is this quadcopter is going to be flying around and it's probably going to crash. When it crashes, what's going to hit the ground first? So that's what you're seeing here with this circle, and it's saying move the camera closer to the flight controller stack. The whole point of that and idea and reason behind that is that this camera will not hit the ground first, right? Because it's probably one of the more expensive components on our quadcopter, and it's probably one of the more fragile components. So we definitely don't want that to hit the ground first. So we moved it down and in just so that it doesn't hit the propeller. I mean, just so the propellers hit the ground first, or even the shell itself. Some other things that, right, if you're going to be applying this to manufacturing, some other things you might want to consider are what contact forces will this part need to withstand, right? Is it going to need to resist or have some sort of abrasive wear, resist some abrasive wear? Is it going to be bolted, right? Is it something, you know, need to consider the bolt forces? All things you might want to consider. Some other things that we considered, right, are specifically with our propellers. So as Brilliant just mentioned, we chose a pretty aggressive propeller and motor. So this thing, because we want this thing to go as fast as possible. So these propellers are going to be moving at very, very high speeds and can be pretty dangerous. So we had to be careful, but it can also be self-harming, right? So we want to make sure none of the wires or components get in the way of this propellers. So that's what you're seeing here, the dimensions of the slots right there, and those are actually for strapping the battery to the bottom. This way that the battery and all of its wires are completely out of the way of the propellers themselves. This dimension, you'll probably see when we show the actual printed part, it did get a little bit smaller just so the battery doesn't slip if it falls.
Okay, thanks, Dan. And some other things that we need to consider were some of the loading conditions. So like I said before, we went with a racing quadcopter frame. So we wanted to really slice the arms down. We wanted to have those a nice thick arm, but then also a thin arm because the quadcopter is going to be slicing through the air as it travels. So we wanted to have some aerodynamic aspects to the quadcopter frame, but we also wanted some sleekness as well. So with that being in mind, we added a fillet to the top and also the bottom edge of the quadcopter frame. We also wanted to increase some of the strength, so we added some radiuses and fillets, so we didn't have any hard 90-degree angles which would add to some breakage points and failure points. So as you can see in the arms, we have a very large radius that goes around the arm, as well as the top edge is a fillet the whole way around the top side of the frame. Moving to the outside of one of the arms where the motor's bolted up, we have 3 larger radiuses for cutouts. We want to also watch out for weight as well, because the lighter essentially we can go with the strength built in, we can go faster. So we increase the fillets around the motor bolt pattern, but then we also have an outside radius as well to give us the roundness and also protection around our motors. We got to keep in mind with also the slots for the motors, as well as the bolt pattern as well, and the placement of how far they were going to be pushed in from the outside edge. So we make sure that we didn't have any failing points for these. So these all added into the loading conditions that was, drive some of our prints for the orientation and the placement on the plate.
Great. Some other things that you should consider, right, even in the design phase, is the environmental conditions. So this quadcopter is going to be flying outside, maybe not in the rain like this picture is portraying, but definitely through some trees and through some pretty tight spaces. So one of the things that we considered, as you can see here, these cutouts, they kind of have a dual purpose that isn't necessarily strictly for environmental conditions, right? Those are more for airflow, circulation on the inside, and also to zip tie the antenna to the back. But when we made these cutouts, they had a very, very sharp point right here. I don't know if you can see my mouse, right on that kind of inner 90-degree angle. And with that point, right, it's very prone to snagging leaves or branches. So we made sure that that was filleted and, wasn't poking out at all, and it won't snag anything. Some other things that you might want to consider in manufacturing: is this going to be in a very harsh chemical exposure, immersed in any sort of fluid, right? These are things that you want to consider, right? Might drive some of the material you're using, or even if it's applicable, right, to even go through with the print. And the last thing we wanted to consider.
So some other things we want to consider here was also some of our specifications that we're going to use in our quadcopter. And this would apply to you out in the industry if you're using any kind of 3D part for any proto testing. So some of the things that we had to look at were the tolerances for the holes. So we use all 3mm hardware the whole way around for the quadcopter. So we wanted to make sure that we had a little bit of a tolerance there, so we could actually slide our bolts through the holes without having to do any post-processing or dremeling out of those holes. In the center of our frame, in the lower left-hand corner, we have a 4-bolt pattern for electronics, as I was saying before. So we can incorporate a smaller mini electronics as well as full size electronics. So this gives the versatility to use whatever kind of electrical components that we purchased. And then something also to think about is we use continuous fiber, carbon fiber, in with this print for more of a just a stronger, robust, nice, stiff frame when we're hitting those high speeds and cutting through the air. So if you can see the vertical slots in the lower left-hand corner, we had those pushed out a little bit farther. Those are for Velcro straps to strap the battery down to the bottom of the frame. Now we had those slots a little bit further out to the edge, and we had to have a minimum of 2.4 millimeters from the edge. That's actually what we had before. We had to have a minimum of 2.8 millimeters, and we pushed that in, and we actually went with over 3 millimeters for that continuous fiber to run the whole way around the frame, which we'll explain just a little bit later. In the upper right-hand corner, we'll now zoom into one of the arms for where the motor is going to bolt in. Now, I went over this just briefly before, but some of the specifications we got to keep in mind is we went with a 16 millimeter diameter as well as a 19 millimeter diameter. What that will give us is the flexibility for multiple size motors for this racing class frame. So we can incorporate, a smaller motor, or we can really kick up the performance and go with a larger, higher kilovolt motor if we wish. Something else we had to consider is also the bolt tolerance here that fit through the slots. Make sure we had enough room for those bolts, as well as the outside 30 millimeter diameter for the motors. We wanted just enough material on the outside of the motors, so if we did crash, we're actually hitting the frame and not hitting more expensive components like the motor. So those were some of the specification we had to consider.
All right. So now that we had the design done, you're ready to print. So let's kind of go over the 3D printing process and kind of some things that you might want to consider during this configuring and printing stage. So we have our CAD model. We're going to send that to an STL file, which is then going to be put into the slicer, and then you're going to slice that part in that software, and that software is going to create a code and send it to the printer to be printed. And in each of these stages, you're going to have different things you want to consider. Lots of things you got to consider. So from CAD to STL, some of the main things you want to think about is, it wasn't really applicable to us, but if you have a multi-body part or an assembly and it's all in one file, you're going to want to make sure that you export those bodies and those parts individually, right? You don't want to export them as one file. I mean, there's rare occasions, but most of the time you're going to want to export as individual files, right? Because if you don't, it may look like there's multiple bodies in your STL file when you open it up in whatever CAD software you're using. But once you send it to the printer, if there's any coincident mate or any coincidence between those two, if they're touching at all, they're going to fix together and fuse together and be printed as one part. So that's something you want to consider. Another thing you want to consider is the size of the file. So what you're seeing here on the right side is I bumped up the settings all the way up to the finest mesh settings that we can get for the frame. And it's a pretty simple file, and even that got up to 282 megabytes, which is very large. If you don't know, it's big. Most slicers not going to be able to handle that. So just keep in mind how big of a file you're creating. Right? It's kind of a trade-off. Smaller mesh, smaller triangles gets more accurate representation of curved surfaces, but if it's too fine, going to be able to even print it because it's just going to crash the software. So something you want to consider.
Okay, and then something else that we had to consider when we put the parts through the slicer. These are images that we gathered from the slicer. To go over first was our part orientation. So first we'll go over the upper right-hand corner image. So if you can look at that part there, the build plate is flat as if you were sitting at a desk, and the frame is turned up towards the ceiling. So it's rotated 90 degrees and his arms are facing the ceiling. So we had to figure out which way is the best way for us to print, this part and get the most strength, but also have to keep in mind how much material we're going to use and how long it's going to take. So the purple lines that you see is actually support material generated in the slicer. So as I said before, you can't begin printing just in midair. You need something underneath it to support it, which will be the support material. So that one would not be the most functional way to print that frame, pointing up in the air and just having the least bit of surface area to actually hold that print on the printing bed. So what we went with is the lower left-hand corner. As you can see, if that frame was just laying flat on a table, that's exactly how it's laying on the printing bed. It was laying completely flat, coming down from the Z-axis, your nozzles going back and forth and printing those layers. So we didn't need to generate any support material for that. We had minimum layer height. And then also with our part fill, we didn't have any part fill in this orientation because the print's going to be completely flat. All right, and then also looks like we just lost our PowerPoint there, but let me see what we could do to get that back. But we also had to keep in mind our continuous fiber going around our print as well. We had our continuous fiber going the whole way around that print, so we had to keep that in mind too, because the continuous fiber is going the whole way around the outside edge. If our quadcopter is traveling forward, it's going to give it the most strength in the axis that it's traveling, opposed to the other axis. So continuous fiber was also another huge thing that we had to keep in mind. Hey Dan, are you still there?
I'll get in contact with Dan Breland. Oh, there we are. He's connecting to audio. Just making sure that we're fielding all the Q&As if you want to take a look on there.
Sure. Yeah, let's take a look at that.
Yeah, I don't know why I got kicked. That was weird.
All right. So we're back. Can everyone see our screen again here? Okay.
Yes, we can.
All right. So just to finish up where I was at with the continuous fiber in the lower left-hand image, the blue lines are representing the continuous fiber that's going around the outside edge of that quadcopter frame. So that continuous fiber is going to add strength to our frame. So, and the gray part is going to be our other filament material. So what we're saying in this image here is that our slicer is going to be, our part in the slicer is going to be printed the best on flat on its back in the Z-axis, flat on the printing plate.
Yeah, and moving on to the continuous fiber, like Breland was just mentioning, if you're not familiar, continuous fiber is what sets Mark Forged apart. Really, it allows you to really boost up your strength and reinforce pretty areas that you really need to have and experience some high forces. So what we did, you're kind of seeing what a first go at lining our in the blue line right here. First go at lining the fiber through the frame. Right, but if you're not familiar, adding fiber can add up to 22 times stronger in the XY plane, specifically in that layers, in the layers that you're adding them, right? Because when you're putting a bending force, right, it's going to put these fibers in tension. And if you think about the continuous fiber, they're very strong in tension, right? But it's not going to add it in the Z-axis because you're only adding it in those layers. So you're not reinforcing in between those layers. You're only reinforcing that specific layer that you're adding the fiber in. So that's why print orientation plays an even bigger role when you're looking at adding continuous fiber to your part. And it might even, you might even look to split up your part if you need to have your part printed in one orientation for one specific reason, but you need to withhold or withstand a force that's kind of contradicting that orientation. You might even want to look into splitting the part so you can actually withhold that force or that load. So if you want more information on the fibers, definitely go check out and talk to the trade booth. But the fiber that we chose to use was carbon fiber. It was a close call between either carbon fiber or Kevlar. We ended up going with carbon fiber because of its weight. It's a lot lighter than Kevlar. So Kevlar is a bit stronger, but it's not, we wanted it to be as light as possible because we want our quadcopter to be as fast as possible. So some of the properties of carbon fiber are its high stiffness and high strength to weight ratio, which is the main reason why we chose carbon fiber. its failure behavior, right? It's going to be stiff until it fractures. So its ideal loading condition is constant loading, which isn't our application. But like I said, we chose carbon fiber because of its high strength to weight ratio, right? It's a lot lighter and similar strength, although Kevlar is a bit stronger. But you can see here on the right, we have this link that was, you've probably seen a video of it. It's lined with carbon fiber. If you haven't, definitely Google it, Markforged carbon fiber Instron challenge. You'll see a cool video. It goes up to, I think, almost 22,000 pounds before breaking, which is just shows how strong this is, how much strength it's actually adding to your parts.
There's also a cool video in the Markforged booth, Dan, where you see people trying to break apart. So another reason to check that out. Yeah.
Yeah, it's hard. I've tried. I've stepped on it. It's not possible, at least for me. But yeah, that's it. We designed. That's our journey through our quadcopter. Right. I'll show you some renderings that we did of it. Really did the renderings. You might have give us a little comment on it.
Sure. Thanks, Dan. So in this rendering, the first rendering we see here, it just applied appearance, a couple reflections on the surface of the quadcopter. We were trying to push it through Visualize just to give it a pretty cool perspective, a final appearance. We weren't sure where it would be after printing all the parts, if we could make it get everything completed in time for MIP. But these are just some of the renderings that we went through here, and they turned out pretty nice, I think.
Yeah, we added a nice background, kind of the racing background here, and we have this kind of banking around a turn, kind of showing how it would look like if it was flying around turning.
Right. And all these were done in SOLIDWORKS Visualize.
All right. Well, that's pretty much all we have. Are there any questions that we didn't get to answer?
Dan, it looks like there is a question here from Rusty. I believe, Rusty, what you're asking with racing quads or drones, why is there not protection around the blades opposed to just the canopy itself? I believe, correct me if I'm wrong, but think of the quadcopter as essentially a race car. It's made for racing, so everything you're trying to strip down everything that you can. So like with a race car, only proprietary parts are going to be put on the car. Added material around each one of the blades, which are all 4 blades, they're going to add up over time. Plus, also you have to think about working on the quadcopter. So anytime you have to change props, just snap a prop. It's a lot easier to snap a prop, and you want to protect your electronics instead of just your props because they're a lot cheaper to replace. Hope that answers your question.
Yeah, we have a build of it. We printed it, so we do plan on having. We didn't think of doing a video, but probably be a great idea.
Sorry, Dan. I'm just gonna for the people who might not have seen that. Somebody asked, are you guys still planning on building it? And will you have a video? If you do, be cool to see the final design. To which Dan and Breland are saying, we're doing it.
Breland actually has the 3D printed part. We got it printed the other day, so we can.
Yes, with our background, it might show up kind of strange, but we can produce some extra pictures and stuff for you guys. I'll hold a little bit closer to the camera. I know our background is going to kind of affect some of that in the way, but this was the canopy that we provided. It's not going to come in exactly right. Let's try to turn the orientation here.
I might be able to get a picture of it. I think you sent me one. Right,
but we'll post some pictures. The quad actually came out very nice, very nice. Here you go. There you go, Dan. Great. These are some of the pictures I was able to get out yesterday. We got it just in time. So we had some mixed feelings with the canopy design, with going with the turtle, but that's something for a future project that we'll work on, and we're probably going to develop a little bit here. So yeah, that has the kind of design behind it as well.
It's sort of like a hybrid, right? So racing, but also kind of looks like a turtle, right? For going for full on racing, I'll probably slim that down as little material as possible.
As a marketer, I appreciate the design in blue there. Very, very nice. We do have somebody that asked something through the chat opposed to the Q&A. I want to make sure we don't lose sight of it. They said, and it's a good one, do you change your print strategy and orientation based upon the material you choose, i.e. metal versus plastic versus carbon fiber? And thank you, Dale. It is an awesome print.
Thank you. Thank you. Yes, I can answer that really quickly. Yes, we definitely will change the prints depending on what type of material we're using. As we were showing before, we use continuous carbon fiber with the frame. So with that continuous carbon fiber, we want to place the quadcopter frame flat on its back to make sure that we had continuous fiber going the whole way around in the correct orientation. We could turn it on the other axis, but we would use a lot more material just to support the frame if it was turned 90 degrees in the XY.
And to answer for metal versus plastic, that does, for the most part, it's going to be very similar, but there would be times where you would change it because of the sintering process that the metal would take during the atom process, right? Because it's got to be self-balancing. So if it's not able to be balanced the way it's printed, right, you might want to consider a different orientation because it might collapse, or because it's pretty malleable when it's going through that sintering process.
Absolutely.
Any other questions? Q&A or the chat will do. Dan and Breland are ready for you, so speak now, guys and gals.
And our emails are here too, if you want. But
yeah, feel free to reach out and ask us any other questions.
All right. Oh.
All right.
Nope,
Thanks.
Just kidding. There's another one. Do you have a cheat sheet for recommendations on print orientations?
We have, so Markforged does have something available that's online that will help you if you just, I can probably find that for you if you are interested. It's their design guide.
That might be a great idea to put something together, Dan, also internally. So yeah, I mean, we can answer any of your questions as well through this tech support as well if you guys have any questions.
I was just going to say that's an excellent idea. I smell some marketing content being created. But you can definitely go ahead and email either Dan or Breland, or check us out on the booth. We'll remember you by name, and you can go ahead and ask us a little bit more about that. We'd be more than happy to address some of that. And somebody asked, did we talk about generative design and how it fits with additive?
We didn't talk about that for this presentation, no.
Do you want to add a few nuggets there?
Breland, do you have any nuggets?
I guess what would you be referring to with your design? It would, I mean, that's something we could probably take offline and probably dig in a little bit deeper and explore a little bit more, kind of customize it around your particular application. You could either reach out to us through email or through tech support.
I actually think we have some marketing content on that specific question though, so
great.
That's some good stuff. Yeah, catch us all at the booth. All right, well, if there are no more questions or any more comments, thank you, everyone.
Thank you, everyone, for joining.